Today I'm going to discuss eigenvalues and eigenvectors of Paulis matrices, or we can call this topic spin vectors for spin-half systems. The eigenvectors of spin matrices Sx, Sy, Sz can be obtained by writing the eigenvalue equation. Since the matrices are 2 by 2, the eigenvectors must be column vectors with two compounds. The eigenvalue equation for Sz with the eigenvalues h cross divided by 2. So for example, here I am taking Sx equal to 1 divided by 2 h cross 0 1 1 0. This is Sx and Sy h cross divided by 2 0 minus I 0 Sz equal to h cross divided by 2 1 0 0 minus 1. So these are the Pauli matrix Sx, Sy, and Sz. So here we want to find eigenvalues and eigenvectors of this Pauli matrices. First I am going to find eigenvalues. Eigenvalues of Sx. Sx is equal to h cross divided by 2 0 1 1 0, right? So here I am going to find the eigenvalues of this Pauli matrix. So now Es Ax minus lambda I equal to 0. So therefore we can write Sx. This one is I'm writing one like this: 0 h cross divided by 2 h cross divided by 2 0. Okay, this is Sx. This is eigenvalue equation formula, right? To find eigenvalue equation, a minus lambda I equal to 0. Here A is the matrix of the given element. So here Sx is the given element. I am using here Sx. 0 h cross divided by 2 h cross divided by 2 0 minus lambda into unit matrix 1 0 0 1 equal to 0. So now simplify this equation. Minus lambda h cross divided by 2, right? This one h cross divided by 2 minus lambda. Okay, equal to 0. So then multiply these two things. Lambda square minus h cross square divided by 4 equal to 0. Then lambda square equal to h cross square divided by 4. Therefore, lambda equal to plus or minus h cross divided by 2. So these are the eigenvalues of the Pauli matrix, Sx Pauli matrix. Similarly, you can try these two components Sy equal to plus or minus h cross divided by 2, Sz plus or minus h cross divided by 2. So this is the eigenvalues of this Pauli matrix. Next, eigenvectors of spin-half system. Okay, here I'm going to explain eigenvectors of spin-half systems. So for simplicity case, I'm going to take first Sz. Sz equal to h cross divided by 2, 1 0 0 minus 1. 1 0 0 minus 1. We want to find eigenvectors of this spin-half system. So before explaining this, I want to explain one thing to you. If an operator A is applying on a wave function, it gives the same wave function multiplied by some constant value. This constant value is called eigen value of system. This wave function is called eigen function of system or eigenvector of the system. Here I'm going to apply, this is the operator. Here I'm considering this one is the operator. This is the operator A. I'm going to apply this operator on this wave function. I can get same wave function and some values here. Okay. H cross divided by 2, 1, 0, 0, minus 1. This is operator. Okay. This is operator. I'm going to apply this operator on A1 and A2 ket vector. Okay, this is ket vector for wave function. Here I'm going to get same. This is operator A. This is function, right? By using this eigenvalue equation. This is alpha. Same wave function. A1 and A2. And I got here H cross divided by 2. Okay, this is just eigenvalue equation. Okay, so now I'm going to apply these things on this function. Operator is applying on this wave function or ket function, then I can get some value. Let us see. H cross divided by 2. After applying this one, what we can get here? A1, this one, minus A2, right? Equal to 1 divided by 2 H cross A1 and A2. So both are same, right? Can get cancelled. So you got this one. A1 minus A2 equal to A1, A2. So what does this mean? A1 equal to A1. This is one equation. A2 is equal to minus A2. This is another equation. By using this equation, we can get A2 is equal to 0. From normalization condition, psi star is equal to 1. Here, what is psi? This is psi, right? A1, A2. So we know ket vector represented column vector, bar vectors, row vectors. A1, A2. So this is psi. This is psi star. A1, A2. This is ket vector, right? This is raw vector equal to 1. So after multiply these two things, we get A1 square plus A2 square equal to 1. Then I'm going to use A2 here. a1 square is equal to 1, a1 is equal to 0, right? a2 equal to 0. So here we got two eigenvectors. One is 0, another one is 1. The eigenvectors of matrix Sz corresponding to the eigenvalues. So this word is very important. The eigenvectors of the matrix Sx corresponding to eigenvalue h cross divided by 2. Then the eigenvectors of this corresponding eigenvalue of Sz, not Sx. Sz operator is this one. So be careful here. Here I am applying eigenvalue here, h cross divided by 2. So no, we know eigenvalues Sz is equal to plus or minus h cross divided by 2. Here already told, right? Lambda is equal to Sz is equal to h cross divided by 2. If you apply here h cross divided by 2, then you can get eigenvectors 1, 0. If you apply the same procedure here, minus h cross divided by 2 instead of h cross divided by 2, in case if you apply minus h cross divided by 2, then you can get 0, 1 eigenvector. This is eigenvector. This is eigenvector. So therefore, S Z Pauli matrix eigenvalues plus or minus h cross divided by 2. Sz matrix eigenvectors 1, 0, 0, 1. Eigenvalues, eigenvectors. So these eigenvectors are denoted by the alpha and beta. Alpha is equal to 1, 0, beta equal to 0, 1, and usually they are called spin up and spin down states. This is a spin up state, this is spin down state. These two component eigenvectors of spin half Pauli matrices sometimes can call the spinners. Next, I am going to calculate eigenvectors of Sx Pauli matrix H cross divided by 2, 0, 1, 1, 0. This is Sx. Here I am going to calculate eigenvectors of this matrix. So this is operator 0, 1, 1, 0. This is operator cat A1 and A2. Here I am taking cat A1 and A2. We know cat vectors are represented column vectors. This one is A1 and A2. This is simply eigenvalue equation. Okay. This is operator O cap. This is wave function. Okay. This is energy value, eigenvalue. This is wave function. So you always remember this eigenvalue equation when you are solving eigenvectors or spin-half systems. So this is the eigenvalue equation of spin X matrix. So this is operator. Here I am using this operator. This is the wave function. One is the, for example, here is the one is there. One is the eigenvalue of the spin. We take this one in case h cross 1 by divided by 2. You can get h cross 1 by divided by 2. So here I am not taking this h cross divided by 2. So I can use in the end of this derivation h cross divided by 2. Okay. So now we can apply. So after applying this operator on this wave function, we can get A2, right? Here A1, right? Equal to A1 and A2. So next step, this one. Just wait. Okay, now it is better. So after this one, this is the next step. So from this equation, we got A2 is equal to A1. A1 is equal to A2. So now you can use normalized condition. Normalized condition. Psi star is equal to 1, right? A1, A2, psi star means bra vector. We can write A1 and A2 equal to 1. Then A1 square plus A2 square is equal to 1. Here, observe carefully. A1 square plus A1 square equal to 1. Since A1 is equal to A2, here I am applying. See what I am getting here. A1 square is equal to 1. a1 square is equal to 1 divided by 2. a1 is equal to how much? 1 divided by root 2. Okay. And similarly, if you use a2 is equal to a1, you got a2 is equal to 1 divided by root 2. These are the eigenvectors of Sx matrix. Next, very important one, this one. Eigenvectors of Sy. H cross divided by 2, 0 minus I 0. Okay. So again here I'm using eigenvalue equation. Here I'm taking 0 minus I 0 is the operator. So a1 a2 are the ket vectors. a1 a2. So then a1 a2. This is eigenvalue equation of the system. So now I'm going to apply this operator on this ket vector. So I got here minus I a2, and this one is the a1 I a1. So this one and this one, right? Okay. a1 a2. So here we got minus I a2 is equal to a1, one equation, and I a1 equal to a2. So from normalization condition, here everybody is doing some mistake. Psi star equal to 1, right? A1 a2. So a1 a2, right? That is equal to 1. So here what is the norm of this equation? Modulus of square is equal to 1, right? So here I am using the modulus. So generally people using this equation, right? a1 square plus a2 square is equal. If you use this condition, you can't get the answer. So you need to use this condition, norm of this condition, equal to 1. Then you can get the answer. Okay. So first I'm going to use a2 is equal to ia1. A1 square modulus plus, in place of a2 I'm going to use I a1 modulus square, not inside outs. Okay. Equal to 1. 2 a1 square is equal to 1, then a1 is equal to 1 divided by root 2. And similarly, in case if you use other condition, you can get a2 is equal to I divided by root 2. So these are the a1 is equal to 1 divided by root 2, a2 is equal to I divided by root 2. So these are the eigenvalues and eigenvectors of in-half system.